All right, here's section 5.6, writing sine and cosine functions, and then talking about applications of them. So we'll start with writing sine and cosine functions. It's super simple, I promise. If you remember, we have our standard form of the sine and cosine functions. And then A changed the amplitude. B changes the period. C changes the phase shift. And then D is a vertical shift, midline shift. So our formula for period, 2 pi over the absolute value of B. If I want to solve for B, I multiply both sides by B and divide both sides by omega. So my formula for B, 2 pi over the period, omega. So that's going to be helpful. Because in our first example, letter A, we are going to take our period, which we are given is pi over 2, and then find B is 2 pi over the period. Dividing by a fraction is the same as multiplying by the reciprocal, so my new period is actually, or my B value, is 4. Let's try letter B. 2 pi over the period, which they told me was 4 pi. So B is going to be 1/2. Go ahead and try C on your own. Pretty straightforward, I think. That's why I'm kind of rushing through this. Now, if I have both the period and the phase shift, if we were starting with a function, then I would need to factor out the B value and so on. But in this case, I'm starting with B and C. So it's a little easier coming this direction. The period is pi over 2. So B is 2 pi over 2, which we just found up here is 4. And then there's a horizontal shift, pi to the right. So in my parentheses, whatever this function ends up being, I have 4, my B value, times x. Pi to the right is going to be subtracting pi. I do the opposite. And then if I wanted to, I could distribute this 4x minus 4 pi. That's going to be my answer. Because we're just looking for the parentheses in the equation. So go ahead and try letter C. I'll leave these other problems here for extra practice. I can totally talk about them with you if you want to come in on your own. But I know you like shorter videos, so I'm going to keep this as brief as possible. Example 3. Now I need the cosine function that has an amplitude of 2. So what's A? It's going to be 2. Period of 3 pi, so B is 2 pi over 3 pi, 2 over 3. A phase shift of pi over 2 to the left, so C, pi over 2 to the left means that's plus pi over 2. And then vertical shift up 1, so plus 1. So y equals 2 times the cosine of 2 over 3 x plus pi over 2 plus 1. And then I can simplify what's inside the parentheses. 2 over 3x plus pi over 3 plus 1. Try example 4 on your own. Okay. Now, great question would be, well, how do I know if A is going to be positive or negative, right? Or B for that matter. You would be given, like in example 4, the one I'm asking you to do, you would be told that it's reflecting over the x or the y-axis. So you would know whether to make those positive or negative. All right, I'm going to try or do example 5 for you, and then I'm going to leave more practice. You don't have to do it, but I'm going to leave it for you as some extra practice. So we can also do this when given a graph. So if I'm given this graph, I'm starting here and I'm going up, so I'm going to say this should be a sine function. My amplitude, I see right away, is 2. My height from the midline is 2. So I know A is 2. I haven't been flipped, so it's not negative. There's no phase shift from what I can tell. The graph isn't shifted any to the left or to the right. It's not moved up or down. The midline is still the x-axis. And then I'm going from 0 to 2 pi. So my b is still 1. My period is still 2 pi. So it looks like this is the equation of this function that's been graphed. That's basically it for writing sine and cosine functions. Again, more practice if you'd like, but I'm going to jump right into why I just taught you how to write sine and cosine functions, and that is because we can apply these things. Crazy, right? We can apply sine and cosine functions to real-world situations. So let's take a look at that. We went through all of these in class. I'm going to go through them right now with you in this video, in case you were absent or you were stuck. So example 1, the tides in a particular bay can be modeled with an equation of the form d equals a cosine of bt plus c, where t represents the number of hours since high tide and d represents the depth of water in the bay. The maximum depth of water is 36 feet, the minimum depth of water is 22 feet, and high tide is hit every 12 hours. My goodness, that's a lot of information. But that's nice. The more information they give us, the easier this is for us. So, T is the number of hours since high tide. What that tells me right away is that at time equals 0, I am starting at high tide. High tide will be where there's the maximum depth of water, in this case 36. So here's my first point. Because for letter A, they want us to sketch a graph of this situation. High tide is hit every 12 hours. That's my period. That's how often it takes this to repeat. So 12. 24, so we can see 2 full periods. And after 12 hours, I'm going to be back at 36 feet. We know the sine and cosine functions are nice, smooth curves. They're continuous. Halfway through my period, then, is where I will be at my minimum, which is 22 feet. There's my graph. So these are high tides. Here's low tide. And then I need to determine the values of A, B, and C so that I can write a formula, write the equation for this function. Well, A will change with the amplitude. What is my amplitude? Well, I first need to know my midline. That's going to be halfway between 22 and 36, which is 29. 36 minus 22 divided by 2. That'll give you your midline. So A is from 29 up to 36, or from 22 to 29. That's 7. B is 2 pi divided by the period, which we said was 12. So pi over 6 is B. And then C is the, in this case, it's unfortunate that they use this letter. That would be how we've been talking about D, which is the midline shift. I moved the midline up 29. So my function is D equals 7 times the cosine of pi over 6t plus 29. And then it says you can check your work in your calculator. We talked about how to do that in class. Just plug this in. Make sure you're in radian mode since we have a pi over 6 in there. And you'll be able to see that this is the right graph. This is the right function. Fantastic. Let's keep moving on. We'll look at number 2. The height of a yo-yo above the ground can be modeled using the equation, I don't feel like reading it, where h represents the height of the yo-yo in feet above the ground, and t represents time in seconds since the yo-yo was first dropped from its maximum height. So we want to know the maximum and minimum heights that the yo-yo reaches above the ground. This is a lot easier than you might think. Max and min for a cosine graph or a sine graph, well, it's either the very top of a wave or the very bottom of the wave. And we know that for the sine and cosine functions, the very top of the wave, the highest any wave will ever be, so for this function here, the most that can ever be for any cosine function is positive 1, right? The range is from -1 to 1, so the max output I can ever get from that is 1, and the minimum output I can ever get from that is -1. So to find the maximum height, h equals 1.75 times, take that whole function, the most it will ever give me is 1 plus 2.25, that's 4 feet. The minimum, the least that function will ever give me is -1. So the minimum height above the ground is 1/2, half a foot. Okay, sine and cosine always works that way, max and min. And then for b, how much time does it take for the yo-yo to return to the maximum height for the first time? I'm starting at its maximum height, right? I'm holding it in my hand, and then I drop it, and then it comes back up. That is one full cycle, one full period. So I'm really looking for period. B equals pi. I'm taking that from my equation. So period is 2 pi over pi, which is 2 seconds. They gave me a unit in time, seconds. So the period for this graph, for this function, for this situation, is 2 seconds. Let's talk about Ferris wheels now. I'm going to let you read this on your own, so if you want to pause this, go ahead and read through it, and then unpause it, and I'm going to get started right now. First, I know that my period, one full rotation, is 8. So my period is 8 minutes. And that I'm starting at 5 feet above the ground. So I'm starting here. And then one full rotation in 8 minutes puts me back there. And then my highest point, 130 feet above the ground, is going to be halfway in between. So at 4. So there's my graph. It's a poor graph, I do apologize. So I need to find my amplitude. It's a little better. I need to find my A, B, and C. So let's start with amplitude. I need from the midline, so what's halfway through this wave? Well, 130 divided by, or 130 minus 5 divided by 2 is going to be 62.5. But that's just the halfway distance between these two numbers. I actually need to add 5 since I'm measuring this distance from 0. So 67.5 is the midway point, midline, which means my amplitude is 62.5. But that's the amplitude. What about A? Is A positive or negative? I'm using cosine to model this situation. Cosine usually starts at its maximum and goes down. Here I'm starting at a minimum and going up. So what that tells me is that this cosine function has been reflected over the x-axis. It's been flipped over. So that means A is negative. B is 2 pi over the period. The period is 8, so that simplifies to pi over 4. And then C, I shifted the midline up 67.5 feet. So my function is y equals negative 62.5 cosine of pi over 4t plus 67.5. Not too bad if we stop and think about it. We're just working backwards. We're taking a situation and information and writing a graph, writing a function for the graph. One more example problem for this section. Good, we're only at about 15 minutes. I did try to keep this short. I'll let you read through this, but basically we're looking at the temperature in an office. The temperature varies according to this sinusoidal function, um, where y is the temperature in Celsius and x is the time in hours past midnight. A fun aside, sinusoidal, one of my favorite words, is in fact connected to the word sinus. Sinus is Latin for a curve, and when they translated the works of the Greeks and the Arabs um, on trigonometry, they used the word sinus to describe the curves, these graphs, the waves. So the sine wave, that's where we get sine, cosine, um, sinusoidal. And sinus, that's used to describe, from Latin, the hollow curves in your head. So I thought that was so interesting, but my classes didn't seem to. So now you all get to hear about me say this, get to hear me saying this once again. Anyway, back to the problem. What is the temperature in the office at 9 a.m. when the employees come to work? X is the time in hours past midnight. So 9 a.m. means x equals 9. All I have to do is plug into this function. This is a straight evaluating question. Y equals 19 plus 6 times the sine of pi over 2, 9 minus 11. 9 minus 11 is negative 2. Negative 2 times pi over 2 is negative pi. So this is 19 plus 6 times the sine of negative pi. The sine of negative pi, that's the same as the sine of pi. My point here means that sine is 0. So 19 plus 6 times 0, which is 19 degrees Celsius at 9 a.m. Not too bad. And then what are the max and min temperatures in the office? Again, the most that this sine function right here will ever give me as an output is positive 1. So the maximum is going to be y equals 19 plus 6 times 1, or 25 degrees Celsius. The minimum value that that sine function will ever give me is negative 1. So plug in negative 1 for that whole function, and I get 13 degrees Celsius. A little cold, actually, but not our concern. So, word problems. These are the kinds of word problems you'll see. Writing functions from them, evaluating, finding max or min values. I love these kinds of problems. It's just mind-blowing to me that we can use trigonometry to describe these completely different situations. It's so fascinating. If you have questions, please do let me know. Rewatch parts of this video that confuse you, do some practice on your own, do the practice problems from class, and get ready for your assessments. Thank you so much and have a good day.